We are jumping straight into Categorical Flow Maps by Dan Roos, Oscar Davis, Floor Eichelboom, and colleagues from the University of Amsterdam and Oxford. This preprint just dropped in February 2026, and it targets what is probably the single most annoying bottleneck in generative AI right now.
Oh, yeah. The speed limit of discrete data.
It's the autoregressive bottleneck.
Exactly.
So if you want to generate text or, graphs or molecules, you're usually stuck. You're either generating one token at a time, which is just painfully slow, or you're wrestling with these discrete diffusion models that are incredibly hard to speed up.
Right. And we've seen continuous flow matching just completely change the game for images, right? We've got real-time generation now. But it historically just breaks when you try to apply it to discrete categories. It just hates the probability simplex.
Which brings us to the big solution in this paper, Categorical Flow Maps, or CFM.
Yeah, it's a method that treats this discrete generation problem as a continuous flow, but, and this is the key, it strictly constrains it to that probability simplex.
And they pull this off with two really core innovations. The first one is endpoint parametrization.
So instead of learning a velocity field that might, shoot off into the void, the model predicts the final discrete category, predicts the endpoint, and just interpolates directly towards it.
And the second big idea?
That would be ECLD. It stands for Endpoint Consistent Lagrangian Distillation. It's basically a whole new objective function. It throws out the standard mean squared error loss, which makes zero sense for categories, and replaces it with a cross-entropy-based loss.
So it actually aligns the training with the kind of data you're using.
Precisely.
And the results are, well, they're pretty significant. They're getting state-of-the-art one-step generation for molecules on QM9 and ZINC.
And really strong few-step performance on text benchmarks like TextAt8 and LM1B. It's beating the existing discrete flow and diffusion baselines pretty handily.
So this is effectively bringing that whole flow matching revolution over to language and biology.
It's a fundamental shift, I think, in how we're going to handle discrete generative modeling.
Okay, that's the 1-minute summary. Now let's really tear this apart, because for the engineers and researchers listening, the devil is absolutely in the geometry here. Let's start with the context. We've seen consistency models, flow matching, they've taken over images. We can get these incredible 124 by 1024 pictures in 1 or 2 steps. So why has text been left behind? Why is ChatGPT still streaming out one word at a time?
Well, it really comes down to the fundamental difference in the data manifold. Images, they essentially live in Euclidean space. Pixel values are continuous. You can have a value of 0.1, 0.2, 0.5. You can slide smoothly between them. And the stuff in the middle still kind of makes sense as like an intensity.
Right. But text is discrete. There's no half word.
Exactly. Text, or say nodes in a graph, they're categorical.
Right.
You're either the token for cat or the token for dog. There is no cat 0.5.
Right.
And when we model this, we use one-hot vectors or, probability distributions. And here's the constraint that breaks everything.
The probabilities have to sum to 1.
The simplex constraint. Geometrically, this forms a simplex. If you have, say, 3 categories, your data lives on a triangle that's just floating in 3D space. If you try to apply standard continuous flow matching, which learns a velocity field in just open Euclidean space, that vector field has no idea the triangle even exists.
So it just tells you to move in a direction that pushes you right off the map.
You shoot right off the simplex. You end up with a vector where the probabilities don't sum to 1, or even worse, some of them go negative.
And once you leave the simplex, your data is it's meaningless.
It's garbage. And until now, the main alternative was discrete diffusion, which uses these Markov chains to just flip categories one by one, step by step.
But Markov chains are inherently sequential, right? You can't just jump to the end easily.
Distilling a Markov chain down into fewer steps is mathematically very messy. The transitions are these sudden jumps. They're not smooth flows. So the authors here basically said, look, we need the speed of flow matching, but we need a flow that actually respects the simplex.
Which brings us to the geometry and parametrization. They introduced this endpoint parametrization. Most flow matching papers I read are obsessed with the velocity field, $5. Why change that?
Because defining velocity on a simplex is really tricky. So instead of asking the model, hey, what direction and speed should I have right now? They ask, where's the destination?
They just predict 6 by Eulers, the end state.
Yes. Even though the whole generation process happens on this continuous timeline from t equals 0 to 1, at every single time step, the model is trying to predict the final, clean, discrete state 6 Attal winners.
Okay, so instead of a compass heading, it's giving you a GPS coordinate for the finish line.
That is the perfect analogy. And here's why that solves the geometry problem. The model outputs a probability distribution, probably through a softmax or something similar, that is guaranteed by its very structure to be on the simplex.
So the destination is valid by definition.
Right. And then the flow is just defined as a simple linear interpolation, a straight line connecting your current noisy state into that predicted valid endpoint.
And if you draw a straight line between 2 points on a simplex,
You stay on the simplex, or, to be more precise with their noise model, you stay within a specific cone of valid probability distributions. Imagine a cone connecting your current state to the entire valid probability face. The trajectory is strictly confined inside that cone. You literally cannot fall off the edge of the world.
that seems incredibly intuitive. If the geometry is that straightforward, why did it take until 2026 to get this to work?
Because while the geometry is clean, training it is an absolute nightmare if you use the wrong loss function. And this is the real technical core of the paper, ECLD.
The distillation breakthrough. The paper mentions that naive distillation just failed. And by naive, I assume they mean using the standard tools we use for images.
Exactly that. In continuous flow matching, especially when you're doing what's called Lagrangian self-distillation, or LSD, you try to minimize the error between a student model, the fast one, and a teacher model, the slow, accurate one. And you usually measure that error using mean squared error, MSE.
Which works just fine for pixel values. A little bit off is a little bit of error.
It works great for regression. But now think about categories. If the true category is cat, which is the vector 1, 0, and your model predicts dog 0, 1, MSE just treats that as a geometric distance. But for categorical data, we care about likelihoods. We care about bits of information.
We want cross-entropy.
We need cross-entropy. Trying to train a probability model with MSE is just, it's so inefficient. It's a regression loss for a classification problem. The gradients don't punish wrong classes sharply enough, and the whole optimization becomes really unstable.
So they needed a way to jam cross-entropy inside a flow matching framework.
And that is endpoint consistent Lagrangian distillation, ECLD. The authors derive this really elegant mathematical bound that allows them to control the error, the residual, using only endpoint predictions. And this lets them just swap out MSE for cross-entropy.
Okay, let's drill down into the loss function itself. It has 2 specific terms.
It does. The first term is endpoint consistency. This basically asks the question, does the student model at times predict the same final outcome as the teacher model at time t's?
So it forces the fast student model to hallucinate the same final reality as the accurate teacher.
Exactly. And it compares those 2 predictions using cross-entropy or KL divergence, which is the native language of discrete data.
And the second term?
That's the temporal drift. It's a regularization term. It minimizes how much the prediction of the final state changes over time. Ideally, if your model is perfect, it should predict the correct final molecule or word right at t0 and never change its mind as it goes to 1.
So if the prediction wobbles, if it thinks it's a cat, then a dog, then a cat again, this temporal drift penalty just slaps it.
Precisely. And this combination endpoint consistency plus that temporal drift regularization is what allows the model to self-distill. In some cases, it doesn't even need a pre-trained teacher. It learns to be a few-step generator completely from scratch.
That's a huge claim. Training a few-step generator from scratch usually leads to, mode collapse or just total instability.
And yet it works here.
Yeah.
And it works because the loss function actually respects the data type. It's using the right tool for the job.
I want to pivot to test time inference. There was this section on steering that really caught my eye. They call it Lookahead.
This is one of the coolest byproducts of predicting the endpoint, of predicting $6.11.
Usually guiding a diffusion model is a pain because you're dealing with all this noise. If I have a noisy graph and I want to ask, is this molecule toxic? A normal classifier is just going to fail.
Right. In standard diffusion, you have to train these special time-dependent classifiers that know how to handle noisy inputs. It's expensive and it's annoying. But with categorical flow maps, at every single step, the model says, hey, I predict the final clean input is this.
It gives you a clean view of the future at every step.
Exactly. So you can take that predicted $6.01, you can feed it into any standard off-the-shelf classifier like a toxicity predictor or a sentiment analyzer, and then calculate the gradient with respect to your desired outcome.
And you just use that gradient to update the trajectory, to nudge it.
Yep, they call it flow map lookahead. You're steering based on the predicted destination, not your current noisy location.
They showed this with binarized MNIST, didn't they?
They did. Say you want to force the model to generate the digit 0. With lookahead, Even if the current state is just noisy static, the model might predict, I think this is going to be a 7. The classifier sees that 7, says, nope, I want a 0, and the gradient immediately shifts the flow towards the 0 cluster in the latent space.
That beats guiding on noise every day of the week.
It's so much more efficient.
Let's get to the numbers then, the experimental results. They started with molecules QM9 and ZINC250K.
And ZINC is the real stress test here. QM9 molecules are pretty small. ZINC has these larger, complex drug-like structures. It's much harder.
And the main metric is validity. Does the model generate a graph that actually obeys the laws of chemistry?
Specifically, they looked at one-step generation. Can you produce a valid ZINC molecule in a single forward pass?
Okay, hit me with the baselines.
MoFlow, which is a previous flow-based baseline, got about 63.1% validity.
Okay, not bad.
PairFlow, a discrete diffusion method, managed only 11.2% validity in one step.
11%, that's basically unusable.
It completely breaks down. Diffusion relies on having many steps to refine the structure. Now CFM, this paper, with the ECLD loss.
What did it get?
93.5% validity.
From 11 to 93, that is not just an improvement, that's an order of magnitude.
It effectively solves one-shot generation for this specific task. And to prove it wasn't just a fluke of the architecture, they ran an ablation study. They used a naive flow map, same architecture, but with the old MSE loss and an unconstrained velocity.
The square peg in the round hole approach.
And it performed significantly worse. It just proves that you need the Simplex constraint and you need the ECLD loss. They aren't just, theoretical niceties. They are absolute requirements for complex discrete data.
Okay, molecules are graphs. Let's talk about the holy grail, text. They tested on text 8 and LM1B.
Yep. This is where it gets really interesting for the LLM crowd. They use an architecture that's based on the DIT, the diffusion transformer, which is pretty standard for images now.
But they had to hack it a bit, right? I saw the paper mentions some specific engineering tweaks.
They did. A key detail is that they actually removed the softmax from the input embedding layer of the DIT.
Wait, hold on. Usually you softmax the input to turn it into probabilities. Why would you remove it?
They found that applying softmax right at the beginning actually caused severe underfitting. It was squashing the signal too much too early before the model could process it. By removing it, they let the raw logit values flow into the transformer, and the performance jumped. They also swapped out layer norm for RMS norm.
Ah, standard stability hacks. So how did it do?
The performance was really strong. In what they call the low NFE regime, we're talking 1 to 4 generation steps, they beat DFM, which is discrete flow matching, and UDLM, the unified discrete linear model.
So for very, very fast text generation, CFM is the new leader.
It is.
But
I do have to point out a little caveat that was mentioned in the results for the LM1B dataset.
there's always a trade-off.
The entropy was lower than the baselines.
Translate that for me. What does that mean?
Entropy is a measure of diversity or randomness. If your entropy is low, it means the model is kind of playing it safe. It's predicting the most likely common words, but it might be missing out on the more diverse, creative long tail of the distribution.
So the sample quality itself, the Gen PPL, was good. The sentences made sense.
Well, the quality was excellent. The text was coherent. But that lower entropy suggests a slight mode collapse. It's possible that forcing the flow to be a straight line on the Simplex is just a little too rigid. Maybe it cuts out some of the complexity you need for really diverse human language.
That is a fascinating point. Maybe the straight line assumption is too simple for the nuances of language.
It's a hypothesis.
Yeah.
But even with that, generating coherent text in 4 steps is a massive leap over generating it token by token, which can take hundreds of steps.
And they also did images, right? Binarized and mist, treating pixels as discrete.
Yep. They got an FID of 10.1 in the single step, which beat the previous few step methods. It just shows the method generalizes. It's not just a graph trick, it's a discrete data trick.
I want to touch on the implementation details because flow matching can be computationally heavy.
For sure. The big cost usually comes from calculating the Jacobian, that huge matrix of all the partial derivatives.
Which scales terribly.
Right. Ideally, you never want to actually calculate the full matrix. So they implemented a JVP kernel, that's Jacobian vector product.
And what does that do exactly?
It lets them compute the product of the Jacobian and a vector directly without ever having to instantiate that massive Jacobian matrix in memory.
Saving memory, I assume.
Huge amounts. They reported a memory reduction of about 50%. And a speed up of around 10% per iteration. This is really crucial because, you can train these models on standard research hardware, not just, massive industrial scale clusters.
They also mentioned dynamic weighting for the loss.
Yes, using the method from Kendall et al. Since you have two big loss terms, the flow matching loss and the distillation loss, balancing them is usually a pain. You have to tune a hyperparameter, a lambda.
And nobody likes tuning lambdas.
Nobody. So they used a learned uncertainty-based weighting. The model basically learns how to weight the terms itself dynamically during training. It makes the whole process much more robust.
So let's synthesize all this. We have a method, Categorical Flow Maps, that finally bridges the gap. We get the speed of continuous flow models, but we finally have the right mathematics, the Simplex constraints, the cross-entropy distillation, that actually respects discrete data structures.
It's a rigorous first-principle solution to a problem that people have just been hacking at with weird workarounds for years.
So the question everyone listening is asking, is this the end of the autoregressive bottleneck? Are we going to see ChatGPT 6 or Llama 5 running on something like this?
I mean, that's the billion-dollar question, isn't it? The quality on LM1B is super promising, but scaling this to a 70 billion parameter model is a totally different beast. That entropy drop we talked about, that needs to be solved to make sure the model can still be creative and not just predictable.
But even if it doesn't replace giant LLMs tomorrow?
For domains like drug discovery, where you need to generate millions of molecule candidates overnight and you care way more about chemical validity than you do about poetic diversity, this is a game changer right now.
It really feels like the dam is cracking. Whether it breaks completely for text remains to be seen, but for structured data, it feels like the flow is already here.
I completely agree. The era of sequential generation for graphs is likely coming to an end.
And that wraps up this deep dive from AI Paper Podcast. If you want to dig into the derivation of that ECLD bound, and it really is a beautiful piece of math, check out the preprint Categorical Flow Maps.
It is definitely worth a read.
See you in the next deep dive into the papers.